Have you ever used a window screen to keep bugs out while letting a cool breeze in? Believe it or not, a very similar idea is used in some of the most advanced technology we have today. These special screens are called frequency selective surfaces, or FSS for short. Instead of blocking bugs, they block invisible waves, like the ones that carry Wi-Fi, radio, or satellite signals. An FSS is like a very smart bouncer at a club. It checks the ID of every electromagnetic wave that comes its way. If the wave has the right frequency, it gets to pass through. If it doesn't, it gets reflected away. It's a filter for signals you can't even see. This ability to filter invisible waves is incredibly important for our modern, connected world. Think about how many different signals are flying through the air right now. You have your phone's 5th-generation signal, your home Wi-Fi, the radio in your car, and signals from satellites high up in space. Without a way to manage them, these signals would all interfere with each other, creating a chaotic mess. FSS help bring order to this chaos. They ensure that an antenna only listens to the specific signal it's supposed to hear, or they can protect sensitive equipment from unwanted interference. They are the invisible traffic cops of the wireless world, making sure every signal gets to where it needs to go without causing a jam. So, what do these magical surfaces actually look like? At their core, they are just repeating patterns of metallic shapes printed or placed on a special sheet. These shapes could be simple squares, crosses, rings, or even more complicated, artistic-looking designs. The specific shape, size, and spacing of these patterns are what determine which frequencies get a pass and which ones get blocked. It's a bit like a key fitting into a lock. Each pattern is designed to be a perfect lock for a specific frequency key. By carefully designing these patterns, engineers can create filters for almost any kind of wireless communication you can imagine, from deep space missions to the smartphone in your pocket. The role of FSS is expanding every day as our technology gets more complex. They are essential for building better satellite communications, creating more efficient wireless power transfer systems, and even for stealth technology, where they can help make an aircraft invisible to certain radar frequencies. They are a fundamental building block in the world of electromagnetics, allowing us to control and manipulate the invisible forces that power so much of our modern lives. The next time your Wi-Fi is working perfectly in a crowded cafe, you might just have a clever little frequency selective surface to thank for it, silently doing its job behind the scenes. For a long time, making these frequency selective surfaces was a big, heavy job. Imagine trying to build that window screen we talked about, but instead of using thin wire, you're using thick, solid metal bars. Early FSS were often made this way by machining or etching metal patterns out of rigid, bulky sheets of material. These traditional FSS were strong and worked very well, but they had some major downsides. They were heavy, clunky, and completely inflexible. You couldn't bend them or wrap them around a curved surface. This made them unsuitable for many modern applications where size, weight, and shape are super important. Think about a satellite that needs to be launched into space. Every single gram of weight costs a lot of money to send into orbit. A heavy, rigid FSS just isn't practical. Or what about wearable technology? You can't exactly strap a stiff metal plate to your arm. The old way of making FSS was like building furniture out of solid stone. It was durable, but you wouldn't want to carry it around with you. This limitation meant that engineers could only use FSS in places where they had plenty of space and didn't have to worry about weight or a curved shape, which really restricted their potential for new and exciting inventions. But now, we have an amazing new way to make them: printing. Just like you can use an inkjet printer to put ink on a piece of paper, scientists and engineers can now use special printers to lay down patterns of conductive materials onto thin, flexible sheets. Instead of regular ink, they use nano-inks filled with tiny particles of silver. This ink is printed onto a flexible base material, like a type of plastic called polyimide Kapton, which is strong, lightweight, and can handle high temperatures. The result is an FSS that is as thin and flexible as a piece of photographic film. It's a total game changer. This new method completely revolutionizes what we can do with FSS. Because these surfaces are now printed, they are incredibly lightweight and can be made quickly and cheaply. But the best part is their flexibility. You can roll them up, bend them, and wrap them around almost any shape you can think of. This opens up a whole new universe of possibilities. We can now integrate FSS directly onto the curved body of an airplane, wrap them around a satellite antenna, or even build them into flexible electronics and clothing. The heavy, stone-like FSS of the past are being replaced by these light, adaptable, and powerful new designs. So we have these amazing flexible FSS, but what if we could make them even smarter? What if, instead of having a fixed filter that only works for one frequency, we could have a filter that can change its mind? This is where the concept of reconfigurable or tunable FSS comes in, and it's one of the most exciting areas of research. A tunable FSS is like having a bouncer at that club who can change the guest list on the fly. One minute, they're letting in the fifth-generation crowd, and the next, they're switching over to let in satellite signals. This ability to adapt is incredibly powerful for new technology. The secret to making an FSS tunable lies in the material it's printed on, which is called the dielectric substrate. Think of the dielectric as the environment that the electromagnetic wave travels through. Changing this environment can change how the wave behaves. By printing special dielectric materials between the conductive silver patterns, we can change the rules of the filter. One amazing material used for this is a ceramic called Barium Strontium Titanate, or BST. The cool thing about BST is that its properties can be changed just by applying a little bit of electricity to it. It's like having a dimmer switch for the FSS. Let's break down how this works. Every dielectric material has a property called its dielectric constant. You can think of this as how much the material slows down an electromagnetic wave passing through it. When we print our silver patterns on a standard material, the FSS is designed to work perfectly with that material's specific dielectric constant. But if we can change that constant, we can shift the frequency that the FSS allows through. Applying a voltage to a material like BST changes its dielectric constant, which in turn retunes the FSS to filter a different frequency. This happens almost instantly, without any moving parts. Another way to do this is by using different types of printable materials. For example, engineers can use inks that are mixtures of polymers, like cyclic olefin copolymer, with different ceramic powders. By changing the recipe of this ink, they can create a surface with a precise dielectric constant. This means they can print one FSS designed for one frequency, then print another one right next to it with a slightly different dielectric ink, making it tuned for a different frequency. This gives us incredible control to fine-tune the performance of the surface, making it perfect for the exact job it needs to do. The real magic of these printed, flexible, and tunable FSS is seeing them in action. Their unique properties are solving problems in all kinds of high-tech fields. One of the biggest applications is in advanced antenna systems. For example, in modern 5th generation and future 6th generation communications, we need antennas that can handle many different frequency bands at once. A tunable FSS can be placed over an antenna, acting as a dynamic filter. It can switch frequencies in a split second, allowing a single, simple antenna to communicate on multiple networks, making our devices smaller, more efficient, and more powerful. It's like giving one antenna the superpower to be many antennas at once. Another key area is in building better radomes. A radome is a special cover that protects a radar or antenna from the elements, like rain, ice, and wind. A traditional radome is just a dumb shell, but a smart radome with a flexible FSS built into its surface can do much more. It can be designed to be perfectly transparent to the antenna's operating frequency while blocking any interfering signals from the outside. For stealth aircraft, a tunable FSS on the radome could even change which frequencies it lets through, helping the aircraft adapt to different radar threats and remain hidden. We'll also see them used for electromagnetic shielding. In a hospital, for example, you have sensitive medical equipment that can be disrupted by stray signals from cell phones and Wi-Fi. You could coat the walls of a room with a flexible FSS film tuned to block those specific frequencies, creating a safe, quiet zone for the equipment without having to build thick metal walls. Similarly, in a satellite packed with delicate electronics, a lightweight FSS blanket can be wrapped around components to protect them from harmful radiation and interference from other systems on the spacecraft. Looking to the future, the possibilities are endless. Because these FSS are lightweight, flexible, and can be printed, they are perfect for the next generation of technology. Imagine smart windows that can change to block cell signals when you want privacy, or let them through when you want a strong connection. Think about smart clothing with FSS woven into the fabric to optimize the performance of wearable sensors. By giving us the power to precisely control the invisible world of electromagnetic waves, these printed, reconfigurable surfaces are not just an improvement, They are a building block for a smarter, more connected, and more efficient future.